Hello and welcome. This is the Taming Wild AI channel, where we bring AI technologies out of the wild using the best practices of software engineering. In the last video, we saw that the Torchvision library has already brought several computer vision models in from the wild. Well, they've done so at least for inference using pre-trained weights. Today we're going to survey the papers behind some of these models along with their Torchvision source code. This will help us understand the innovations these models represent. In 2014, Google engineers published a paper entitled Going Deeper with Convolutions. The paper featured a model called GoogleNet, maybe GoogleNet. The main innovations of GoogleNet over AlexNet were an increased number, 22, of convolutional layers. Despite this, 1/12 the number of parameters and increased accuracy. The authors observed that increased depth and width of convolutional neural networks increases accuracy. Unfortunately, it also increases the number of parameters. This increases the likelihood of overfitting as well as the computational demands of training the network. They created this inception module. The module has 4 branches whose output is concatenated. Branch 1 outputs a 1-by-1 convolution. Branch 2 outputs a 3-by-3 convolution. Branch 3 is supposed to output a 5-by-5 convolution except for a known bug in this implementation. Branch 4 is a max pooling layer, but the output is run through a 1-by-1 convolution to allow the branch outputs to be concatenated. You'll notice that branches 2 and 3 have a 1-by-1 convolution before the layer with a larger kernel. This serves to reduce the overall computational demands of the module by reducing the number of inputs that would otherwise be passed to the next layer. Concatenating the outputs essentially allows the subsequent layer to learn during training which branches to weight heavily and which to ignore. The idea is to end up with a deep convolutional network. You can see how many inception modules are used here. End up with a deep convolutional network that uses convolutions of various sizes along with max pooling. During training, the network learns whether to weight max pooling or convolution in any inception layer and which size of convolution to weight. In previous networks, these were hyperparameters that required hand tuning. GoogleNet also introduced auxiliary classifiers. As we saw with AlexNet, the convolutional and max pooling layers are intended to generate features from the input, and fully connected layers called classifiers are intended to classify the feature combinations. In GoogleNet, classification layers similar to the output layers were added as branches to the lower layers. The loss function of the network incorporated the loss at these lower layers in addition to the output layers. The intent was to improve the discriminative capability of the lower layers. The auxiliary classifiers were unused during inference. For more details on the inception module, check out Andrew Eng's videos on the topic in the episode notes. In the same year, the Oxford Visual Geometry Group published a paper entitled Very Deep Convolutional Networks for Large-Scale Image Recognition. In this paper, they evaluated networks of increasing numbers of layers. They discovered that increased depth resulted in significantly increased accuracy, even using small 3-by-3 convolutional kernels. However, VGGNet does employ approximately 3 times as many parameters as AlexNet. In the Torchvision source code, you can see the list of network configurations named A, B, D, and E, just as they are in the paper. I like how the network constructor parses these configurations. When it encounters a number, it creates a conv2d layer with a kernel size of 3 and that number of output channels. When it encounters the letter M, it creates a max pooling layer. This allows easy experimentation with configurations in addition to those published in the paper. Once the configuration is parsed, the initializer of the VGG class adds an adaptive average pooling layer and some fully connected linear layers with dropout. For more details on dropout, check out Udacity's video on the topic in the episode notes. In 2015, researchers at Microsoft published a paper entitled Deep Residual Learning for Image Recognition. Previous work, like GoogleNet and VGG, had found that increasing the number of convolutional and pooling layers increased the accuracy of the trained network. The authors tested the limits of this idea by trying very deep models. They discovered that training a model with large numbers of layers actually resulted in a degradation of accuracy. This was puzzling. Suppose you have a model with some number of layers that gives you the optimal accuracy. Now suppose you add layers to the model to create an augmented model and then train that. The additional layers should end up performing the identity function, basically just copy the input to the output without any modification. The augmented model should still have the optimal accuracy, certainly not lower accuracy. The authors supposed that there may be some difficulty with the convolutional and max pooling layers getting trained to perform the identity function. Therefore, they explicitly introduced skip connections in the network. The skip connection obviously performs the identity function. It gets added to the output of the skipped layers. If the identity function is required for the overall module, then the skipped layers can end up outputting zeros in all cases. This turned out to be a much easier function to train compared to the identity function. If a different function is required for the overall module, the skipped layers can end up calculating residuals, delta values that should be added or subtracted from the input for the desired result. This block of layers is implemented in the basic block class, which adds the input to the output of convolutional and batch normalization layers. Batch normalization looks at the range of values present in a batch of data. It shifts and scales the input values based on this range. Batch normalization was studied in another 2015 paper entitled Batch Normalization: Accelerating Deep Network Training by Reducing Internal Covariate Shift. It was discovered to have a number of benefits. It makes the network less sensitive to the initial values of the weights. It lets the network train at a higher learning rate and therefore converge faster. And it has a regularizing effect, meaning the network is more likely to generalize appropriately instead of overfitting to the training data. For more details on ResNet, check out Connor Shorten's video on the architecture in the episode notes. For more details on batch normalization, check out Code Emporium's video on the topic in the episode notes. At the same time that ResNet was published, researchers at Google published a paper entitled Rethinking the Inception Architecture for Computer Vision. They explored ways to make convolutional networks deeper and therefore more accurate, but they wanted to do this without unnecessarily increasing the number of parameters and the computational cost of training them. The first method they employed was factoring large convolutions. This means a 5 by 5 or even 7 by 7 convolutional layer is replaced by multiple layers with smaller kernels. The next method they experimented with was asymmetric convolutions. This means a convolutional layer with an n by n kernel is replaced by a 1 by n layer followed by an n by 1 layer. They found that this helps, but not if it is used in layers near the input to the network. The third method they experimented with was increasing the stride of convolutional and pooling layers to reduce the size of the grid being analyzed by the network. The network called Inception v2 used method 3 in layers near the input and various combinations of methods 1 and 2 after that. The fourth method they experimented with was label smoothing. This means altering the ground truth labels during training. The resulting model is less confident about its predictions and therefore less likely to overfit to the training data. The network called Inception v3 used all of these methods in addition to factorized 7 by 7 convolutional layers and batch normalization in auxiliary classifiers. You can see the Torchvision implementation of Inception v3 using increased stride layers near the input and Inception A, B, C, D, and E layers after that. Inception A has 4 branches similar to the original GoogleNet architecture. Inception B replaced a 5 by 5 convolution with 2 3 by 3 convolutions. Inceptions C, D, and E have asymmetric kernel sizes, including 1 by 7, 7 by 1, 1 by 3, and 3 by 1. In 2017, researchers at Google published a paper entitled Mobile Nets: Efficient Convolutional Neural Networks for Mobile Vision Applications. They were thinking about robotics, automated driving, and augmented reality applications. These applications required computer vision to be performed at a high speed and on processors with low power, memory, and computational capacity, at least compared to what you might have on a workstation or a data center server. Google's work focused not on increasing accuracy, but on the size and speed of computer vision networks. They built on the Inception architecture and introduced 2 hyperparameters. These allowed trading a model's accuracy in exchange for speed or reduction in size. A standard convolution filters and combines inputs into a new set of outputs in a single step. MobileNet is based on depth-wise separable convolutions implemented here. Depth-wise separable convolutions split a standard convolution into 2 layers: a depth-wise convolution for filtering each input channel and a 1 by 1 point-wise convolution for combining the outputs. This factorization of the standard convolution drastically reduces the number of computations and the model size. In 2019, Google published a paper entitled MobileNet v2: Inverted Residuals and Linear Bottlenecks. In this paper, they introduced the use of residuals, implemented here. The other classification models in the Torchvision library use a couple of specific techniques. I want to cover these techniques in their own videos before resuming the survey. MobileNet v3 and some others were designed not entirely by hand, but using an automated technique called neural architecture search. We'll cover this in the next episode. Other models use a component called a transformer that was originally developed for natural language processing. In this episode, we surveyed some of the models in the Torchvision library and looked at how their key innovations were implemented. These models represent experiments with factorization, residual connections, auxiliary classifiers, batch normalization, and asymmetric convolutions. These techniques allowed for deeper neural networks with better classification accuracy, but without overwhelming the computational limits of specific hardware. Thanks so much for tuning into this episode. If you found it instructive or useful, please share it with others who might as well. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.